We've been talking about acid and base titration, and on the screen is a titration curve, and without reading that it says weak acid with a strong base, how could you tell right away that this titration curve represents weak acid titrated with a strong base? Right, you don't see that straight up at the equivalence point. That's the first signal. How do you know you started with an acid period?
It starts low but not super low.
Right, it starts low but not super low. And you finish high. Okay? So weak acid with a strong base. And the one thing that I see a lot of that I didn't harp on in my notes that much, and this is what that Pogel packet did, if you looked at the titration curves, and all of the answers to that, my answers, are posted, and I did warn you to watch that Model 4 curve, because that was not a well-drawn curve from the publisher, and we talked about why that was the case. It's probably a little hard to generate these, although you'll be generating them in the lab. It'll work really nicely. In any event, where is the equivalence point?
Above 7.
Its pH will be above 7, and if you had to point to it on the graph, would you point here or here?
Here.
Right here. So what volume of base did you add?
22.
About 22 mils, okay? So these are all things you want to recognize right away. The region with maximum buffering would be where you're plateauing, right? Because you're not seeing major fluctuations in pH. The pH is relatively constant or maintained within plus or minus 1 pH unit. Are you good there? All right, this is going to be, let me see if I can do it this way. Here we go. Where is pH equal to pKa? At the half equivalence point. So if it was 22 mils at the equivalence point, what volume of base would you have at the half equivalence point? About 11, okay? pH depends only on concentration of conjugate base. That is at the equivalence point, right? Because you have neutralized all the weak acid with the strong base. pH depends only on the amount of excess strong base, would be after. Good. And that's all we've got there. All right? So you have to be able to recognize the curves and know what happens along the way. And we'll take another look at that. I believe I had done the diprotic one with you, but I'm going to reiterate because, again, didn't do much of this. But this is the one I referred to in your notes and your homework, but we all know how homework goes sometimes. So, in regard to 103, how do you know this is a diprotic acid? You have 2 equivalence points. Okay. So you would need an indicator that changes color in 2 areas, and we'll come back to that in just a minute. When you have not added any sodium hydroxide, you're right here. What's the only species that you have at that point if you have the diprotic acid initially? The diprotic acid. And I'm going to try to figure out how I can. That should work, as long as nothing moves. Okay, so in the first one, you have your diprotic acid, and this is just any generic acid. And what do you generate? Well, I didn't add it to water, so if you, no, that's fine. Let's do it that way. Probably should always add it. With the acids, I usually don't, but it doesn't matter. You probably should. I'm just lazy. So we're going to have hydronium ion, which you know because this is a weak acid, and right? Okay? 1 ionizable proton at a time. You're good? Come on, Hannah, you can do this. You need to sleep at night.
I will.
You're so tired.
Always.
Okay, so that's going to be the first curve. So initially, all you have here is diprotic acid. At the half equivalence point, which two have equal concentrations?
The conjugate.
This and that, right? Because you know at the half equivalence point, you've got pH is equal to pKa, which means in regard to Henderson-Hasselbalch, the concentration of the conjugate base and the weak diprotic acid must have been equal because the log of 1 is 0, and so these two are equal. Yes? Yes, yes? So at the half equivalence point here, these two amounts are equal. Okay. At the equivalence point now, the first equivalence point, you will have neutralized all of this, and this will determine the pH. Yes? Okay. So what happens in the second part of the curve? What's your second ionization?
The second H.
So you're going to use the HaHa, right? Add it to water, and what will you make? Okay, so now what you're looking at is the second titration, if you will. And at the equivalence point, the second equivalence point, what are you going to use in regard to determining pH? What will hydrolyze at that point? A2 minus. So if you look at this, keep in mind that Ka1 will be greater than Ka2. So this substance will be present in the highest amount. This substance will be present in the lowest amount because the first ionization is relatively weak and the second one is even weaker. So those are things to consider as well. I hope you don't see too much with diprotics, triprotics, although you're probably going to see one question, but I don't think it'll be the part 2. I think you'll see it in a multiple choice guess-a-roni.
At the equivalence point, when you change the equation,
Which equivalence point here, or just in general?
just in general,
Okay.
what does it change to?
So if you were looking at the first equivalence point, all you would have is this after you neutralize this.
We can't see.
Where is that? Here?
Yeah.
You would have this plus water. And now what's going to happen here is you are going to have it act as a base. Like that. And this is going to be very tricky for you because the diprotic could go either way. So hold your question, and when we do weak base with strong acid, I'll point that out and we'll compare and contrast it with the weak acid. I can answer your question if you want now, and I will because it's bothering you, but the diprotic piece is trickier, and I think your question is more of a, I'm having trouble holding the book and leaning this, it's like shaking. Your question is a little bit trickier with the diprotic piece. If, for example, you had acetic acid, and initially you added strong base, and you got this, and this. Are you with me so far?
Yeah.
Okay. So all along you were running, ooh, that couldn't have been good. All along you were running that particular reaction and you were just doing Henderson-Hasselbalch to get pH. When you're at the equivalence point, you will have neutralized all of the weak acid and all you will have is this. So that second equation will be the conjugate base plus the water, and now the only thing this can do is accept, and so you would have this and this, and this is where initially you were always dealing with Ka, and now you're going to deal with Kb. And what you're going to see today is initially you'll just have been dealing with Kb, and then you'll flip to Ka. And when you do the pre-labs, you'll see both of those, and you'll drive it home.
Is that just the reversible reaction?
It looks like it. But what you have here is a neutralization reaction, and what you have here is hydrolysis.
Okay.
Or ionization, maybe the better way to go here. So, yeah, it looks like it, but just be careful.
Okay.
All right. The other thing I wanted to point out to you before we do the weak base with the strong acid is as follows. There are a few practice exams that have been released, and you will be taking some of these to prepare for the AP exam come April. We'll get through at least 2, and for some of you, you may want to come in and do more. This was a practice exam that was released when they first redid the whole curriculum. I actually thought this practice exam was harder than anything else they released, for what it's worth. But when I first saw these types of questions, I just cringed, because we had never seen anything quite like this before. Previously, it was all math. You just dug into it with the math, you figured it out, you worked through it, it wasn't a problem. And then all of a sudden, it became very, very conceptual. And that's why with some of the homework problems that I know some of you don't even look at, you'll see a little bit of it in AP Insight, but that's what I'm trying to stress and why I went back over the curves. So if you look here, clearly you have a weak acid with a strong base. The sodium hydroxide is the titrant. They didn't use that term here, but I've seen it in newer exams, which is why I really made sure you understood that the titrant goes in the burette and the analyte is what's in the collecting vessel, which is either an Erlenmeyer flask, or when you do your labs, you'll use a beaker, because it's the only way to get the pH meter in there. It says a 50 ml sample of an acid, HA, of unknown molarity is titrated, and the pH of the resulting solution is measured with a pH meter and graphed as a function of the volume of 0.100 molar sodium hydroxide added. Now, I can't print these questions out to you and give them to you, because it's only for classroom use. Okay. So at point R in the titration, which of the following species has the highest concentration? Before we jump on that, let's make sure that we know where we're at every step of the way. So in Q, what's the only species that's present? HA. What's the half equivalence point? Good, because you know the equivalence point's at 40. So at S is when those two concentrations, HA and A minus, are equal. So before that, what are you going to have more of? The HA or the A minus? HA. Okay. So what you're looking at here at point R, which of the following species has the highest concentration? It's got to be HA. You're still there. Okay?
What about the hydronium ion?
And that's a good question. In regard to the hydronium ion, remember that you are when you're considering the hydronium ion initially for the weak acid, you know that the concentration of hydronium ion is considerably less than the concentration of the weak acid, because the hydronium ion will be X, and you are always just slashing out the minus X because it's inconsequential, and as a result, it's got to be significantly less. You haven't generated it enough. Now, if you were talking about a strong acid, that'd be something different. And then in regard to hydroxide ion, same thing there. What you want to consider is how much hydroxide ion you've actually added. So you haven't neutralized all of it, so you couldn't possibly have as much hydroxide ion as you do weak acid. So those are both good questions.
So at point S, A minus is equal to HA?
Correct. Concentrations up, yes. Okay. Now it says, which of the following is the best particulate representation of the species other than water that are present in significant concentrations at U? At U, what do you have in excess?
The base.
The base, the strong base, the hydroxide ion, correct? Look at those diagrams, and without driving yourself nuts, what does it have to be? B. It's the only one with hydroxide ion. So now you're getting a feel for how the questions can be asked, and it's tricky. And like I said, when I first saw this back in 2013, I'm like, there's no math. Where's the math? Give me math. Give me math. And I hated it. And I still hate it. But you have to get used to the conceptual aspect of it. All right. This is going to be a little tricky. I'm going to show you just how computer savvy I am. Not that computer savvy, obviously. But I'm going to be good. I'm going to show you. Pretty good, huh? That's good. Are you proud of me? At what point on the titration curve, this one's tricky, is A minus closest to 2 times that of HA? This one's tricky, so I really want you to think about it. So you know it is not going to be R. You know it's not going to be S. So you're down to 2. And this is what you're going to find on the AP exam. You're very often going to get down to 2 answers. Then you're going to be like, gut check, and go with it. So what do you think it is, Drew? It is T. All right?
At U, would that weak acid be 0?
You've neutralized all of it. Maybe. I guess so. I'm not sure.
'Cause then
I think there's probably, I hate to see 0. I want to say that the question becomes is, all right, so you pop it in. I don't want to say 0 because it's an equilibrium reaction, so it
so
can...
is it always?
It can chop back and, it can flow back and forth a little bit, so I don't want to use 0. But it's going to be minimal, minimal, minimal. But let me think more about that. I don't want to say 0. I hate questions where 0 and always, and so I don't want to say that because you have an equilibrium reaction, so you can go back and forth. So I don't want to say that. But it's got to be negligible.
So at U, A minus would be more than twice that of HA?
For sure.
Like a lot more?
Yeah, for sure. Has to be. All right, and then 17's a little funky too. It says a student carries out the same titration but uses an indicator instead of a pH meter. If the indicator changes color slightly past the equivalence point, what will the student obtain for the calculated concentration of the acid? Okay, so in regard to the base, you had 0.1 molar and you added 40 mils. So that would be 4 millimoles of strong base, correct? What do you know about millimoles of strong base and weak acid? You're going to neutralize all of it at the equivalence point, right? So they have to be the same. So that means you have 4 millimoles of weak acid. What else did they tell you about the weak acid? I gotta move my little drawing, it's in the way. They told you the volume, so it was 50. And this point didn't seem to be clear to a couple kids in my other class, so I want to hammer it. So in regard to the base, we said that we had 0.100 molar times 40 mils, correct? And that's going to be 4 millimoles of hydroxide ion, and therefore we know there's going to be 4 millimoles of weak acid. We know that the volume of HA is 4, no it wasn't, it was 50 mils, right? Yeah. So the concentration of the HA then would be what? Or should have been what? 4. Now keep in mind this is non-calculator, right? Right? So some of you are like, oh crap, I can't do this. Think fractions. You know that this is the same as this. Right? And that would just be that. There's an M at the end there. Do you see how I did the math in my head without sitting there and making a little 50 goes into 4 thing? You don't have time to do that. So think tenths, think 100ths. You've got to think back to like baby 6th grade math, and you've just got to think along those lines. Okay. So the concentration should be 0.08, 00 molar. You with me there? Or has the ship sailed and you didn't get on? You're good? Okay. Now, read critically, and you are much better at this than I. It says he used an indicator and the color changes slightly past the equivalence point. What will the student obtain? So you know you're at A or B, and again, you're down to 2 answers now, which is good. You've got a 50-50 shot, which is better than 1 and 4. So he added a little more base than he should have, correct? So what do you think?
Because as you move past the equivalence point, doesn't the concentration decrease?
So he added a little more base than he should have. That's going to make these erroneously high. And the answer is B. Very, very tricky. And when I saw this set of questions, it bothered me. It bothers me every year. I've got to really, really think through. Your questions won't be this difficult. You will work through this practice exam in great detail. This to me is harder than anything you will see. But there are no straight up easy questions. I still put a few on your quizzes and tests just to keep you sane, but these higher level questions are what they're going to hit you with, and you can always get down to 2, but really think through. In addition, keep in mind 60 multiple choice questions, 90 minutes. You really only have 1.5 minutes per question. and we've now spent 15 minutes doing 4. So we're trying to really make it so you can jump on it and figure out what's going on quickly. And you'll see some of these types of questions in your practice quiz. All right? The other question that I wanted to hit is also in here, and this was a part 2 question. I did this with period 7 early, and I held it on you guys because we did it and they didn't really get it, and I think it's because they didn't have a good grasp of Henderson-Hasselbalch yet. Couple things I want to mention again. With Henderson-Hasselbalch, you have pH is equal to pKa plus the log of the conjugate base over the weak acid. And what you'll see when we do our next big problem after this one is that POH is equal to pKb plus the log of the conjugate acid. I'm trying to think how to represent it. I'm just going to write it in. Over the weak base. And I mentioned this one here because we're going to get to that when we finish up the notes. We have one big problem to go through. We can go through it together, or I can start to walk you through whatever you need to be successful. But in regard to this question, now I'm very, very mathematical. I can only think of things in terms of math. I can do all the problems and then figure out what the concept is. For some of you, you may go the other way. Like I said, it's really just what fits. But this was the only way I could approach this. If pH is greater than pKa, and I was so stupid with it, I had to put numbers in. So for example, let's say this is 5, and this is 3. You need the log of that fraction to be what? 2. Okay. The log of a number that's greater than 1 is equal to a positive value, correct? Throw the log of 4 in your calculator. What do you get? What is it? 0.602? Okay, so it's a positive number, yes? Fine. The log of a fraction is a negative number, correct? So we know that the log of 4 is 0.602, and the log of 1 over 4 is negative 0.602. Yes? Okay? This is going to come back in electrochem too, which is why I'm hitting it here. In order for this number to be greater than 2, the concentration of what has to be greater? The conjugate, right? The numerator. In order for this to be a fraction, this concentration has to be greater, correct? Okay, keep that in mind. We talked about indicators, and when we go back to our titration curves, I want to link it back to indicators. I wrote it, and I want to make sure we do it for a few questions, because that's in your pre-lab as well. So we've got HIN, an indicator, reacting with water. Remember, an indicator is a weak acid. You're going to generate its conjugate base, which is a different color, and this is exactly what we did in the demo the other day, to generate hydronium ion. it says the indicator is a weak acid with a pKa value of 5. It reacts with water as represented in the equation above. Consider the two beakers below. Each beaker has a layer of colorless oil, a non-polar solvent. What dissolves in a non-polar solvent? Non-polar solutes. The only type of IMFs would be LDFs, all right? In beaker X, the pH is 3, and in beaker Y, the pH is 7. A small amount of indicator is placed in both beakers. The mixtures are stirred, and the oil and water layers are allowed to separate. What is the predominant form of HIN in the aqueous buffer in beaker Y? The acid form or the conjugate base form? Explain your reasoning. Right. This would be a short question on the AP exam worth 4 points. And now you're going to see you're either going to know it or you're going to try and fake it. Think about some of the things that I said with pH and pKa. And that's going to drive you home. So in beaker Y, the pH is greater than the pKa, right? The pH is greater than the pKa. So you need this fraction to be positive, which means which species has higher concentration? The conjugate base. So in this instance, the conjugate base form is the predominant form of the indicator. And that's because the pH is greater than the pKa. And you can explain it in terms of Henderson-Hasselbalch. There's nothing wrong with that. Alternatively, you can indicate with the pH being greater than the pKa, the forward reaction is favored, hence ion minus concentration would be greater than the acid form. In beaker X, and I'll show you what they write at the end, and I also can go back to the other. I don't usually always look at what they write, but I should. In beaker X, the oil layer is yellow, whereas in beaker Y, the oil layer is colorless. Explain these observations in terms of both acid-base equilibria and interparticle forces. And they're writing interparticle instead of intermolecular in case you have more of an ion dipole situation. So if this layer turns yellow, would it be HIN there or ion minus and Y? Has to be HIN because the ion would have been water soluble, correct? The fact that HIN, the fact that the oil layer is yellow indicates that the HIN dissolved in it because what you're dealing with there is now the pH is less than the pKa, so the HIN is the predominant form, and it turns the oil layer yellow because they interact through what type of IMF? LDF. Okay? Very, very tricky type question. And again, you know how to do it great, and you don't know how to do it, and it's a big mess. Let me fly to the answers there. So let's see what they wrote compared. And again, my answers very often are mathematical based because that's how I think. It says the conjugate base form is the predominant form. This is because the pH is greater than the pKa, causing equilibrium to form significant amounts of product, ion minus. So again, and you can do it off the math as well. At a pH of 3, the acid form predominates in the aqueous layer because pH is less than pKa. It's a neutral molecule, so it can dissolve in the oil layer because of the London dispersion interactions. This substance is charged, so it preferentially dissolves in the aqueous layer, ion dipole. That's what we had indicated.
When pH is greater than pKa, does
if you have a weak acid. I hope so. Yeah, sounds right. All right. Now, well, I don't know if you want to. I don't think we will go back on. Well, actually, Tiffany had a question there. Let's see if we can hit that. This was your question. And I'm glad I said what I did. Remember you said at point U, will it be 0? And the answer is no. You neutralize all of it. But again, with that equilibrium, I'm thinking that 0 is a bad choice. And it says it's therefore very, very small.
Okay.
Puny. So, yeah. My gut, like I said, zeros and always types things I don't usually go with. Okay. What we want to do now is look at titration of a weak base with a strong acid. So this is all going to look backward. Look at the curve. You start high and you go low as you add more and more acid. You've got your equivalence point there. What would be the volume at the half equivalence point? 25 mils. What's the pH at the half equivalence point? 9 and change, and that would be equal to the pKb, okay? So again, be comfortable with the mirror image type curve. What we're going to do here is exactly what we did previously. It says calculate the pH at the following points in the titration of 100 mils of 0.05 molar ammonia, a weak base, with the strong acid, hydrochloric acid, and this is grossly similar to one of the titrations you'll be running in the lab on Monday. Kb is given. The equations are here. Again, this is showing the neutralization reaction. This is the reaction that controls pH, except once you get to the equivalence point, then you're going to have a different reaction, and we'll get to that. You should be able to do A. This is just like the little mini quiz. Take a minute and try and pump through A. The answer's right here, and then I can show you. Yep.
Is this similar to the where the concentration divided by KB is larger than?
Yeah, you'll be good to go there. Just ignore it. Did it come out? Yes, yes, no problem. What about the next piece? That's good. So you're good on A, how about B? And you should be able to do these yourselves now. Everybody got A, right? No issues? Okay, because A was like the little mini quiz. That should not be an issue. Anybody have B done? Don't look up until you're done. Unless you're stuck and you want to. typically wouldn't, but seeing them to you a little more.
So pH equals pKb plus the log.
Yes, and the conjugate on top.
Does that give you the pH or the pOH?
pOH. All right, so how do we do with B? Pretty good? Yes? Mm-hmm.
How do you know which equation to use?
Initially, you're neutralizing, so a neutralization reaction, weak base, strong acid makes the conjugate. This is prior to the half equivalence point. So this is a nice indication where you can see that the concentration of weak base is considerably larger than the ammonium ion concentration. But whenever you're neutralizing, use a neutralization reaction. And then once you're trying to figure out the pH is when you go back to the ionization type reaction, except at the equivalence point, and we'll point that out. We don't really write the second reaction because I like to jump right into Henderson-Hasselbalch. I think it's easier. And this is a good example too, where you see you have a fraction here, a negative value. And so you can tell in this instance that the I don't want to do that on weak base. I think you're going to get confused. But you still have to go in the forward direction. Well, no, actually you're less. I'm not going to go there. All right. What I do want to point out is in C. What do you know about C? It says you've got 25 mils of 0.1 molar HCl. You don't have to do much work on C. What do you know? The equivalence point is at 50 mils. The concentration of the weak base and the strong acid, you're going to be the same at the half equivalence point, but what is the half equivalence point? So the equivalence point here
It's 50.
50 mils of 0.1 molar. So that would be 5 millimoles of acid, correct? So in regard to the base, then, you need 5 millimoles of base at the equivalence point. But at the half equivalence point, you need half as much of that, correct? So how do you know this is the half equivalence point?
Because you have 2.5.
Because you have half as many millimoles in regard to the weak base and the strong acid. So you have half as many millimoles of strong acid as you do of weak base. So this is the half equivalence point. At the half equivalence point, POH is equal to PKB. So right away you know that this is the half equivalence point. Really no major math to do there. This is the one I want to run through with you in great detail.
Is there any sense in like finding Ka from Kb?
Yep, right here. So in regard to C, you know that with C, you had 5 millimoles of base initially. When you have 2.5 millimoles of the acid, which you would with 25 mils and 0.1 molar, that's the half equivalence point where these two are equal. The pH is equal to 14 minus that, or 9.26. Now, in regard to your question, if we look at D, that's the next thing we want to do. It says that we're going to add 50 mils of 0.100 molar hydrochloric acid. So that's going to be 5 millimoles of strong acid, and right away you're like, ooh, the equivalence point. So at the equivalence point, things do change. Let's prove we're at the equivalence point. Again, weak base, and we're going to neutralize it with strong acid, hence this equation. We've had 5 millimoles of this every step of the way, at least initially. We're going to add 5 millimoles. We take it away because we're going to use it. We take it away because we're neutralizing. And then we're going to have 5 millimoles of weak base. What's the total volume here?
Yeah,
150 is correct. So we're going to have 5 divided by 150, and so our concentration, oopsie, is 0.0333 molar. And Nick, this is where your question's going to come in right here. What substance do we have to hydrolyze now? Or dissociate or ionize? What we have. So now we're going to add this to water. And now we don't want a Kb because look, we generated hydronium ions. So now we need a Ka. So we have 0.0333 molar. Again, the Kb is going to be, we're going to switch to Ka. It's going to be small, so we're not going to deal with the x's that are added or subtracted. So Ka KA times KB is equal to KW. We've had the KB the whole time. We're going to need the KA, which is KW over KB. KW is a constant. That's provided to you on the reference sheet, although you don't have time to look stuff up, so there's some stuff you really just need to know. The KB is 1.8 times 10 to the negative 5, so the KA is 5.6 times 10 to the negative 10. And that's going to be equal to x squared over 0.0333. We can eliminate the minus x because KA is so very small. And x now is equal to the hydronium ion concentration. And now we're going to take the square root of that product, x, which is equal to the hydronium ion concentration, is 4.3 times 10 to the negative 6 molar. And the negative log of that is going to be 5.37. And I think the equivalence point type pH questions are the most relevant, most likely what they will ask you. So be comfortable there.
Where did you get the total volume?
We always started with 100 mils of the weak base, and to it we added 50 mils of strong acid. So that's the 150. The other thing I really want to tie in here, and this you're going to see in your lab. The pH at the equivalence point is 5.37. And the reason why you have to do your pre-lab before you do the lab, you have to do it before you come in, because the lab, the actual doing, will take well over an hour. So you need to be prepared, and you need to know what indicator to use. So our pH is 5.37. So if I look at the following grid, 5.37 is about here, and as I slide down, I want an indicator that has a pKa closest to the pH at the equivalence point. I need its range to surround the pH at the equivalence point, and you might have to explain that the way I just said to you. So the indicator that I'm going to select then is probably going to be methyl red, because that indicator undergoes a color change. Its pKa is closest to the pH at the equivalence point of the titration, or you can indicate that its range encompasses the pH at the equivalence point. And on your pre-lab, which you'll be taking a look at, you're going to see that they're going to ask you the same type of question. And be careful here, there's a lot of numbered labs. Your lab is 3.5, selecting indicators. There are some other labs that you can look at, but this is the one that I think works the best. So again, if you had a pH of 5.37, the pKa of methyl red is 4.95, and that's going to be closest to the pH at the equivalence point, and you'll undergo a change from yellow to red. Typically, you want the indicators to undergo changes where they get darker because it's easier to see. If you had a pH at the equivalence point of about 7, you might pick bromothiamyl blue, okay? And you'll see that in the pre-lab. You'll find the pre-lab pretty straightforward because you've been through so much of this. The very last question here is pretty straightforward, and I'll let you try that in a bit. And again, be very careful. You've got to know what the dominant species are along the curve, and that's where the Pogel packet on titration curves I think will really help you. So what we've talked about today, we finished up with titrating a weak base with a strong acid. You have to be comfortable getting the pH anywhere along the way. They're not going to ask you to do all of them. They might ask you to do one of them. You have to be comfortable with what the major species are every point on the curve. That's what we opened up with. And again, you had some homework problems there. You can go back and take a look at them. A lot of them we did in class because I think it's so critical. You've got your AP Insight. You've got 12 questions to do. I promise it'll be worth your while. Do it. You've got homework problems. You've got a lot. And you've got a pre-lab that has to be done before the next class. You can go back and watch the videotape if you want to go back through any of the multiple choice questions, the mini part 2. On your practice quiz, I gave you 2 part 2s. The first one I think is too mathy. The second one I think is more representative of what you might be asked. Prepare yourself well. Quiz is going to be challenging because it's just a challenging concept. So make sure you're very much on top of the acid-base stuff. Questions? You're good? You feel like you're starting to get it? And you just need some practice. All right? AP Chemistry, not a spectator subject. You've got to do, you've got to do, you've got to do. The more you do, the more successful you'll be. Okay.